That assembly, coupled with good manufacturing techniques and good lubrication, is extremely reliable. And really, the century was dominated by the use of this bearing, and we've loaded it up further and further until, of course, we've caused it to fail in due course as well. And the work by Lundberg and Palmgren is absolutely essential in being able to predict the life of such bearings. We continue to test this mechanism to its extreme because we are unable to lubricate it properly and to ensure that we can monitor it properly. And whilst that all ought to be possible, we still lead this particular component to its failure again and again in daily industrial life. One of the major problems that the 19th and early 20th century suffered was system failures relating from boiler explosions in locomotives and in stationary engines. These are complex problems because they aren't just a simple component failing. Of course, boilers contain quite a bit of potential energy, so as a consequence, when they go up, they release a great deal of potential energy. But what was difficult at the start of such processes was to identify what were the root causes. Early engineers were unaware that the lap joints that they riveted into boilers were causing thermal stressing as the shape changed, and that also the chemical process of the advanced temperatures was causing much more rapid oxidation on the inside of the boiler, where you couldn't see it, than would have been expected. That then caused very rapid fatigue failures and catastrophic failures. It's difficult to underestimate just how much damage the impact of boiler explosions caused for about 100 years. And a lot of our regulation and monitoring today really rotates around trying to prevent these kind of failures from occurring. In the immediate pre-war period, there was a great deal of work, particularly in the United States, looking at the management of operations and including maintenance. And one of the key things we see at that period is the separation of the two activities, more or less reporting to board level as two different departments. Also, during that period, there were models formed using statistical distributions, some of them very simple, like the normal or Poisson distributions, but then moving on to more complicated techniques like Weibel's analysis of failures, which led to statistical distributions which could give good predictions of samples of populations failing. But of course, having seen those rapid developments before the war, the key thing after the war was austerity, and we see then recording examples of something that we're seeing extensively today about life extension and reuse. We're seeing an emphasis today on major overhauls and repair, and one of the key factors as well, particularly as the result of the then mass movement of people and equipment, was the standardization. The standardization of the screw thread, for example, had taken place about 50 years earlier in the UK. However, as a result of the war, there were lots of new screw threads of American section which didn't match up to the English section and some of the screws used on the continent. So the ability to interchange parts became more difficult. Some of Baldwin's railway locomotives became scattered around all over the world as a result of war reparations. But the immediate end of the period also saw a very great rise in international exports. And you may think that the image of the steam locomotive on the right is one of a pre-war locomotive. In fact, that's a 1950 export from Manchester to Australia. So, in fact, there was a great deal of production, and one of the key parts of that was emphasis on remote service planning, and the model of the day was to sell engines, sell equipment generally, and then to sell relatively expensive spares and repairs to the buyers. That, of course, is something that we'll see changed in the future. The immediate period after the war also started to see a move towards prevention and diagnostics. Consider, for example, this comparable product to the Bayer-Garrett in the previous image. This is what the Americans were producing at the same time, and there's recorded evidence of how the Rio Grande company were using oil analysis. I should explain what they're doing here. If there are leaks of water or of the return diesel fuel into the engine lubricating oil, then it becomes denatured pretty quick. And the nature of denatured lubricating oil, of course, causes really quite severe damage to the diesel engine, and then it has to be taken out of service, and it might cause permanent damage to large parts of the diesel engine. Whereas if the diesel fuel or any water in the oil can be determined early, then it can be corrected. So this is probably the first recorded example of condition-based maintenance for this type of process. We also start to see a much wider application in some of the key productive areas, like the power sector. I've mentioned boilers already, but steam turbines are long, flexible shafts supported in a range of bearings, and the images show, in the bottom image, the result of a bearing collapse causing a complete failure of a generator, and the kind of damage that can occur if the generator shaft and its rotor start to touch the stator. Huge damage which needn't have occurred if the vibration could be monitored on this device. Other manufacturing areas, like highly productive areas, including paper machines, steel, started to use vibration, as did transport applications like rail and minerals and mining. I have to take another step back to mention a couple of mathematicians. It's pretty clear that the Renaissance engineer Fourier was not particularly interested in mechanical vibration problems as he developed his mathematics and his somewhat outstanding French administrative career. But we remember him particularly in this field for his development of the integral transform, which we call the Fourier transform. He was also working at about the same time as Gauss, who's also credited. What we can do with Fourier's analysis is to turn time series into frequency spectra and help to diagnose them. And there's two examples here. The first one is quite a simple one. It's a musical instrument, which is an oboe, in fact, and you can see the information in that. It's got a series of sine waves added together, whereas when you look at the machine vibration below, then you can see it's quite complex information. It's got an impact, and it's got a lot of noise on top of its vibration signature. When turning that into the frequency domain, we can start to see some more defined information. And each of these peaks represents a frequency, and the higher the peak, the more the amplitude. And what that enables is good diagnosis about the information coupled in the signal, but also phenomena like harmonics, which you see, for example, in the top image, and those harmonics are indicative of square wave type impacts as the oboe produces, and also you can see the much more complex spectrum of the machine below. But there are a number of key frequencies that are of interest to us, and the change of the amplitude of those frequencies is also important. So the ability to tune in on those frequencies has been important for a long time. In 1943, Brühl and Kerr developed the first charge-type accelerometer. There were probably devices beforehand that could detect some form of vibration, but this really formed a seminal change because the reduction in cost of such a device and the ability to start using instruments in the field with electronic devices started to proceed quite rapidly. Early vibration meters were, of course, quite simple. They worked in analog electronics. Typically, their resolution was limited to about a third of an octave. However, they used a radio-type technology to tune in to particular frequencies, and they were able to give distinct on-the-spot measurements. They were, of course, relatively large and heavy and difficult to take out on site, and in the early days almost impossible to record in terms of their instantaneous measurements, but a graph paper and a pencil recorded those signals for posterity. We've done a great deal since, of course. In particular, one of the big changes was the fast Fourier transform. Of course, Fourier gets a mention in the title of this, and it's worth mentioning that probably Gauss beat him to it in terms of publication. They were both working at about the same time. But the heroes of this particular year are Cooley and Tukey, who were working for IBM at the time, and what they were researching was methods of rapidly and using the novel computers of the day to produce this rapid production of a frequency spectrum from a time series. And again, we can't underestimate just how much this impacted the business, because condition monitoring really didn't look back in the 70s after that. It's important as well, though, to consider some of the strategic moves in the 60s and 70s. After the war, Deming's move into Japan to help rejuvenate the Japanese industry led to a distinct Japanese philosophy on the approach of productive maintenance, which led to the total productive maintenance concept. And what this really enabled was the operators on production lines to become maintainers as well. That is, that those people who were using machines and processes daily and seeing the degradation were able to also affect the efficiency of their process and to be able to make an effect quickly. And the clever bit about that was the combination of the organisation of such processes, integrating the operations with maintenance, which really in terms of a formal process hadn't happened before, and the increasing use of technology to try to detect degradation where it could be detected. So that leads to a number of seminal publications. Nakajima recorded the total productive maintenance research in 1971 in the first Japanese book on total productive maintenance. And in 78, Nolan and Heap published the first book on reliability-centered maintenance, which came out of the aero industry. It's also a decade of a great deal of standards preparation. But what it does do is predate some of the later thinking, particularly from Porter's model from 1985 about the value chain, where some of the primary activities of logistics, operations, sales and marketing and servicing actually include the terms maintenance. And the support activities, where you might have placed maintenance beforehand, that's administration, human resources, product development and procurement, are essentially longitudinal activities which are not part of the value chain directly. So you can see there that the idea of maintenance going from a supporting activity into a value contributing activity is an important step forward. One of the big changes from which the sector really hasn't looked back, of course, was the first personal computer. Now, it's important to note that computerized maintenance management systems and some diagnostic activities took place on mainframe computers prior to this. But really this was a quantum leap in the ability of getting processing power on people's desks. And one of the first things it was applied to was the automation of tasks within maintenance management systems. Things like picking out the optimal jobs to do next, picking out the jobs which would have the maximum impact on cost savings and prevention of failure. But also this rapidly moved into technical areas. The use of, for example, thermal imaging had been developed for military applications, and there are innovations going back to the 50s looking at particular sensor types for looking at night vision, for example. But what happened in the 80s was the ability to process these results much more rapidly, to apply, for example, pseudo-color onto black and white images, which is true today, of course, but also the ability of the hardware to interrogate the results from cooled sensors on a focal plane array, where a Peltier cooler is essentially built into the back of the sensor to keep the sensor cool, which is critical for such efficient images.